So moving on to the materials, the absorber formation processes, and the properties. So I'll answer some of your questions in this section here. Whoops. Okay. Here we go. So of course, in a tandem, as in any multi-junction device, one of the most important layer is the absorber. And one of the more important aspects of the properties of the absorber happens to be the band gap. What should the band gaps be? So in this case, we did a calculation based on finite difference time domain calculation, FDTD, which are very, very good, actually. And what we've plotted here are those results. This is the band gap of the bottom device, and this is the band gap of the top device. It's meant to be a three-dimensional contour plot. So coming out of the page, or these different colors represent the efficiency of the tandem. And these are the efficiencies for the different colors. Clearly, you want to be in the green region, where the efficiency is about 30 to 36%. That's because we're taking into account other things that we can best model, things of the kind of recombination, for example, and real-life sheet resistances and things of that kind. So if you look at this, let's take the case that some of you had mentioned. That is using CIGS for the bottom and Telluride for the top. In this case, you would land right within this region right here. Okay. Now, is that good? Yes, it is. If you look at the yellow region, it is about 18 to 24%. Now, the thing to keep in mind is that many calculations, oftentimes, you can't get to the efficiencies given to you by the calculation. We feel that we get to half of that, we're doing pretty well. So at 18 to 24, that would get you to 12%. So on face value, it seems pretty good, but in actuality, it's not as good as you want it to be. So that's with the CIGS and Telluride combination. And that's because Telluride is a 1.5 EV. Now, some of the researchers here at Stanford are working with putting in zinc in there and others to change the band gap of zinc Telluride, for example. And that's a great direction to go. The biggest problem with the 2-6 system is cadmium. You will find that oftentimes in life, logic doesn't win out. And in this case, even though it is a great material system, I love Telluride incidentally, the fact that cadmium is there is a big problem. Japan and other Asian countries have outlawed cadmium, and it's a big problem. So just to give you, if I had my druthers, I'd work with Telluride. But nevertheless, for a tandem device, it sits right here. What we've been able to do for using Chalcopyrites is that we've been able to tune the lower band gap within this region and tune the top band gap actually from here all the way up to here. But I've only circled around where the green region is. So we can tune it within precisely this region. And therefore, that's why we feel that we get to very high efficiencies with our tandem. As I mentioned, we are now at 20% efficiency on a 20 by 20 centimeter square. To be a little more specific, the tandem absorber materials we're looking at here are chalcopyrites. Chalcopyrites are a class of semiconductors with a stoichiometry of 1, 3, and 6. Okay? And they tend to have a tetragonal crystal structure. So you know many of these chalcopyrites. One is copper indium diselenide, which has been around longer. Some of you have been alive. The band gap is 1 EV. And there's copper indium disulfide, which is a band gap of 1.5 EV. If you look at these two and the band gaps, what you would think is that, well, at 1 EV, that's pretty good for the bottom device. 1.5 is just short of what it really needs to be. It needs to be closer to 1.7 EV. But it's also closer to where the Shockley quasar limit needs to be for a single junction device. But it's just a little bit high. So it's sort of in this limbo land for where copper indium disulfide needs to be. So how do we change that? How do we move this up to 1.7 or greater? Well, one way to do this, and these are efforts that other people have done. Right? One way to do this is to dope it with other group 3 elements to replace some of the indium to increase the band gap. And the typical ones people dope this with is gallium and aluminum. So if you look at copper indium diselenide and you dope it with gallium and aluminum, you get this structure here, and the band gap changes from 1 to 1.68, or in the case of aluminum, 1 to 2.67. And you might say, fantastic, why don't we do that? There are a tremendous number of material processing issues with these configurations. One of which is when you use aluminum, is very much enamored of oxygen, and doing the processing is extraordinarily difficult to prevent aluminum oxide from forming. And there are other issues associated with this as well. If you look at the sulfides, if you add gallium in there, you can get from 1.5 to 2.4. Or if you put aluminum there again, you get from 1 to 3.4 UV. These are the standard things people have done to get the band gap right. So what do we use? For the bottom device, we use copper, indium, gallium, and instead of the diselenide, we replace one of the seleniums with sulfur. So we've done it worse. Instead of a quaternary, we have a quaternary material, right? But it turns out that there's a reason for that, and too complex to go into at this point, but I'd be glad to answer that after the discussion. Our top absorber, to answer your question, is a proprietary chalcopyrite that we developed in which we can tune it from 1.45 to 2.45 eV. Unfortunately, that's all I can say at this point. So this shows how we optimize the band gap for the top absorber. These are the transmission spectrum for the top absorber. So you can see basically this is below the band edge, and then as you approach the band edge, the transmission drops. So the band gap happens to be where this drops off at. If you look at where the ideal top absorber needs to be, it's really within this region right here. And if you look at what others have been able to demonstrate, it's right in this region here. And it just makes it to where the top device has to be. Fortunately for us, we've done a lot of material science in which we've been able to tune the band gap from 1.5 eV all the way up to 2.45 eV. So we can do this both, not just for the tandem, also for the triple junction device. Okay. Yes? Yes. And so the problem there, it has to do with the purity of the material, purity in phase. Oftentimes, what you see is that if the absorber is not, for example, if you look at the XRD and you see multiple phases, you oftentimes see that. Sometimes you see Erbach tails that will mess you up. So what's really important is purity of phase to ensure a very sharp cutoff near the band edge. And that's a very good question, because in multi-junction devices, that cutoff needs to be very sharp for reasons that I'm sure you understand. Right? So then let me go over how we make these absorbers. For CIGS, I think all of you are very familiar with one of the best absorber formation process for CIGS is co-evaporation, no question. Right? And this is done by evaporating copper, gallium, and indium in a selenium and or sulfur environment, whether it's H2S or H2SC. And you can do this and this is done either by Newton cells or other things of that kind. You can do this either in 1 step, in 2 steps, or 3 steps. This just happens to be the best way to do that. And of course, you can do it in a way in which you can grade the band gap as well, so you can tailor how the carriers are extracted from the material. But the important point here is that this is a co-evaporation process. It gives you the highest quality absorber, no question at all. The highest quality absorber and the highest efficiency cells if you make CIGS. The unfortunate problem with this is that it's difficult to control the stoichiometry of this method. And it's particularly difficult to control the stoichiometry over a very large area. It's also difficult to control the delivery of the chalcogen very accurately. And perhaps more importantly, from a manufacturing perspective, its reproducibility is very difficult, and the uptime is not very long. It's difficult to scale. In essence, it's very difficult to manufacture. In fact, if you look at and currently exist in terms of the current manufacturers out there, it's very difficult to identify a manufacturer currently doing anything using co-evaporation. So what do we do for the bottom device for normal CIGS? We do, which I'm sure you're familiar with, a 2-step absorber formation process. We use standard equipment. We sputter down metal precursors, copper, gallium, and indium. In fact, actually, we don't sputter gallium per se. We alloy that with copper to make a copper-gallium alloy. We sputter that down, and then we sputter down the indium. And this way, the stoichiometry is determined solely by the thickness of those layers. And therefore, you can see that this is a much better situation because you can sputter very accurately, very precise thicknesses. This is nothing that you can have to invent. People know how to do this over very large areas as well. So after you deposit the metal precursor, then you put that into the oven and you reactively anneal it. You do this in a hydrogen selenide atmosphere, or a hydrogen sulfide atmosphere, or a selenium atmosphere, or a sulfur atmosphere. So you stick it in the oven and you bake it, and out comes the CIGS semiconductor that we use for the bottom device. But what's great about this, what I said, is that the control of the stoichiometry is much better than co-evaporation. It also uses mature, proven, standard processing equipment, sputtering, and furnaces. Later, I'll show you what the problem with this technique is, particularly for the top absorber. So what do we do for the top absorber? Now, at this stage, I can't tell you exactly what it is, but I can tell you this, that we developed a proprietary absorber formation system in which it combines the advantages of co-evaporation and the two-step absorber formation process that we just described. What it has is essentially the high absorber quality from co-evaporation and the manufacturability, reproducibility, and reliability of two-step absorber formation. And later I'll show you the SEM of the absorber, and you can judge for yourself how well that turns out. What's also very useful from a manufacturing perspective is that it's compatible with high-volume inline deposition. Okay. So this is what we're using for the top device. We can also use it for the bottom, which we haven't had a chance to do at this point because we are currently in production with the bottom, but we do not want to make any changes at this point. So let's move on to how do we increase the top device efficiency. We talked about the structure, we talked about the layers. How do we improve the efficiency? So this is a very high level. These are the things that you need to do that we've been working on to improve the efficiency for the top device. Okay? Remember we talked about those two main things to increase the efficiency, right? It's the transmission and the efficiency of top device. I'm talking about the efficiency at this point. So these are the things. Number one, the areal uniformity. That's going to be a common theme here. The areal uniformity has to be very, very good. Number two, it turns out that there's a key impurity for wide bandgap chalcopyrites that will kill you. We have to minimize that. Number three, we have to reduce the interfacial recombination. Number four, we have to maintain the TCO properties through the absorber formation, which is a very caustic environment. Number four, we have to optimize the heterojunction region. And number six, we have to ensure an ohmic contact to the back. And let me ask you, of these six, which one is the most challenging? Which one keeps me up at night? Which one is the most difficult? What would you say that would be? Don't be shy.
So do you have separate contacts between each cells, or you have a tunnel junction?
No tunnel junction. We basically make 4-terminal and 2-terminal devices. So in the 4-terminal, there's not an issue there. For 2 terminals, we current match by a technique that I can't go into, but we can do that and just merely connect the two together. Sorry, not mean to torture you. It turns out that the most difficult challenging is the bottom one, to ensure an ohmic contact. It's extraordinarily difficult, and I'll show you why in a second. By the way, it's not to say the others aren't difficult either, but that's the one that's been most challenging. So the stoichiometric uniformity, as mentioned, these are chalcopyrites, and so we put down metal precursors. So this is a 3-dimensional plot of the stoichiometry in both in an XY plane. This is the stoichiometric ratio, and you see it's reasonably flat. Here's a line out across there. What we've been able to do is increase the uniformity to less than 1% variation over that area. Extremely, extremely important. If all we do is increase the stoichiometric uniformity from 5% to 2%, and from 2% to 1%, the efficiency increases dramatically. For reasons which I think you can understand. It has to do with phase purity. And so we do that, and it works very well for us. Here is the issue of the impurity I was referring to you about, particularly for the wide bandgap chalcopyrites. To give you an idea how dreadful it is, this is a plot of the current density as a function of the concentration of the impurity. And I apologize, I can't tell you what the impurity is, but it took us a long time to figure that out. You would think it wouldn't take us very long, but there are lots of impurities in many things. And we have to figure out which one was the important one. So if you look at this, you see that at the parts per million level, the JSC drops dramatically. Now, we put down precursors using a sputtering process. And this impurity comes in the sputtering target. If you look at most suppliers, their sputtering targets have on the order of 60 ppms of this impurity or higher. That was the standard when we first got started. We were able to work with our suppliers to get it down to about 2 ppm or less. We're working with them to get it down to 1 ppm. This is unprecedented in the PV industry because most people don't really care. They get to 4 nines or 5 nines, and that's sufficient. But if you're at 5 nines, but this impurity is at the 3 ppm level, it will affect your efficiency. It turns out that it does not. When we work with them and we look at over their process in which you're doing this, we suggested some very simple things that could change. They made a big difference. So in many ways, when we do this, we actually look at target vendors as our collaborator, and it works very well for us. Now, the other issue is the interfacial recombination. So as I mentioned, the interfacial recombination is very important for wide bandgap chalcopyrites. And the way you deal with that is to look at what's called the conduction band offset. The conduction band offset is what occurs here between the absorber and the emitter. Okay, so this is the band structure. Here's the valence band, here's the conduction band, and here's the absorber. You can see that as you get closer to where the heterojunction is, the Fermi level is obviously equilibrate there. But in this case, you have a cliff because the conduction band offset drops down. In this case, you have a spike because it goes up a little bit. Now, if I asked you which one of these two would be better, don't worry, I won't torture you. You would almost universally say the cliff will be better because the electron can fall downhill and you can collect the carriers better. Well, it turns out that you would be wrong. It turns out that the cliff actually exacerbates the interfacial recombination. So for this example, we're at 8% efficiency with a cliff here. But if we use a proper spike in the conduction band offset, the efficiency jumps to 13.7% efficiency. Now, why is that? Well, I have to tell you that this is somewhat controversial. I can tell you this, that the current understanding is that if you put a spike in it, you're actually lifting the Fermi level near the heterojunction such that you have a type conversion happening at the heterojunction. That makes it difficult to have interfacial recombination. Of course, the spike can't be too large because what's actually happening here is that some of the carriers are tunneling across the spike. Okay, did you have a question? Or? Oh, I'm sorry. And so you really have to have the spike at the proper energy and the proper width, otherwise everything stops. Right? So and then the question naturally becomes, how do you control the conduction band offset? You control it by the emitter that you use, by looking at what the electron affinity happens to be from the emitter, how it would match up with that of the absorber itself. So we will go through a number of different emitters to control the conduction band offset, to control the efficiency by controlling the interfacial recombination. So here's the problem that's kept me up at night over the last few years, and I'm glad to say that we solved it, so I can sleep now. But the issue is really clear right here. If you look at the structure of the device, you see what the problem is. The device, our absorber is a p-type absorber, which most tend to be because you want the minority carrier to have high mobilities. So it's a p-type absorber. On the back side is an N+ type transparent conductor, and this side is another N+ type transparent conductor with an N-type emitter. So in essence, if you look at this from an electrical engineering perspective, you have two opposing diodes, which is a serious problem. You cannot collect the holes this very effectively to this side. Another way of looking at it is looking at the band structure, and you see that there's a significant barrier at this side if it's not ohmic. So again, looking at an electrical engineering perspective, you need to change this picture to this picture to make it ohmic. Now again, I can't tell you how we actually did that, but I can tell you that we were able to do that by some proprietary treatment of the films. And our current densities are greater than 20 milliamps per square centimeter, which is 80% of the theoretical limit. So it tells you that we've made a major impact in that region. But it's a very important problem, an ohmic contact for a bifacial top device. Okay, so we talked about the efficiency. Now let's talk about the transmission, which is really the more important issue here. So for the transmission, you need to increase the near-infrared transmission of the TCO. You need to increase the below band gap transmission of the absorber. And you need to minimize reflective and scattering losses. So now, of these three, which do you think is the most challenging and important? I'm sorry, I threw a boomerang at you. It turns out all three are important. So let me go through some of them here, right? So first thing is, probably the most interesting problem, that is the TC, the transparent conductor, or in our case, we use a TCO. It has to be highly transmissive in the near infrared, and it has to be lowly resistive or highly conductive. So why is this a problem? Well, because in order to be highly conductive or have low resistivity, you have to have a large carrier density, right? But the large carrier density results in an enormous amount of free carrier absorption. Here's a calculation based on the Drude model in which you increase the carrier density from, I can't really read that, from 50 centimeters squared per volt, oh, excuse me. I mean, as you increase the carrier density, you can see that the efficiency gets significant. So how do we solve this problem? the clue is right here. If you look at the resistivity is given by 1 over the mobility times the carrier density times the electronic charge. Now again, to get to high near-infrared transmission requires low N. But to get to low resistivity requires high N or high mobility. So the way you do this to counteract these two is to get to very high mobilities, extraordinarily high mobilities. So the key again is to get to high transmission, low resistance TCO, you need a TCO with high carrier mobilities. And what we've been able to do is design a different type of TCO material and a different type of deposition to achieve that. And I'll show you that in the next slide.